Warm greetings, my dear children. So, today's topic is the continuation of chemical equilibrium we are going to see. So, already we saw the basic concepts, what are all involved in equilibrium. So, in addition with that, we are going to see. So, mainly you must understand what are all the applications of equilibrium constant. In the last class, we saw what is equilibrium constant, right? So, Kc equal to K, actually K forward by K backward reaction, right? So we've learned about what is the extent, how extent it will be. I taught you like 10 power minus 3 to 10 power plus 3, right? So right now we are going to see the applications of equilibrium constant. So what are all the applications of equilibrium constant? One is reaction coefficient. So the application of the equilibrium constant is the reaction coefficient. What is the reaction coefficient? Let me explain you with this. For any reversible reaction, okay? For any reversible reaction at any stage other than equilibrium, the ratio of molar concentrations, okay? The ratio of molar concentrations of the products to that of the reactants, okay? So here it is ratio of molar concentrations of the products to that of the reactants. Okay, where each concentration's term is raised to the power equal to stoichiometric coefficients to the substance. It is called the reaction coefficient. Okay, Q, it is designated by letter Q. Okay, and then based on, for a general equation, we can write like this. This is the general equation. We can write QZ is equal to concentration, right? Molar concentration of the product to the molar concentration of the reactants. If QC is greater than Kc, then what is the value of Q? It tends to decrease to reach the value of Kc, that is towards the equilibrium I'm talking about. And the reaction proceeds in the reverse direction. This is very important. Definitely you'll be asked. Okay. And then if QC is less than Kc, then it will tend to increase and the reaction will proceed to forward direction. Okay. If QC is equal to Kc, the reaction is at equilibrium. Okay. So these are all explained with some example. You can go through it. Very easy examples only. You must learn about how the reactions are proceeding. Okay. So here it shows very clearly the direction of predicting the direction of the reaction. Okay. How we can predict the direction of the reaction? It is, this is what you are saying. I mean, forward, reverse, and then equilibrium we saw, right? If QZ is less than KC, it is, the direction is forward, right? Less than Kc means the direction is forward. That means the net reaction goes from left to right, reactant to product side. Okay. Then if QC is greater than Kc, then definitely backward reaction, reverse reaction. So from right to left it will be. Okay. So you know reactants, products, right? So based on that, we can able to write the QC and Kc. Okay. If QC is equal to Kc, no net a reaction takes place. That means it is in equilibrium. So this diagram clearly shows. Okay, here QC is less than Kc. Okay, guys, you'll be asked about like case if Kc is greater than QC. This condition is can be reversed like that also. Kc is greater than QC. So both it talks about the forward reaction. Okay, this case QC is greater than Kc. It is backward reaction or reverse reaction. Okay. Okay. So how we can calculate the equilibrium constant? So this reaction, this example, it shows how to calculate, how to predict the reaction is forward, the reaction is backward like that. Calculate QC and compare with the KC. Whether the QC is greater than or equal to or less than, then see this example. The value of KC is given already. You have to find QC, that is the reaction coefficient. Okay. You know that, right? molar concentration of the products to the molar concentration of the reactants. Okay, it is a ratio. Based on that, you can find out the resultant and check with the resultant whether it is greater or lesser. Based on this, you can predict the direction of the reactions, whether it is right to left or, sorry, yeah, right to left means reverse, left to right means forward, okay? Forward direction or reverse direction. Here it shows calculating equilibrium concentrations, right? It is given clearly in your book. What is the first step? So this is very important how you can calculate the equilibrium constants. Okay. There are 5 steps involved. Okay. So it is given very clearly in this. Balanced equations of the reaction is written. First, balanced equation of the reaction is written. Okay. After the balanced equation is written, make a list of the following for all the substances. First list is initial concentration, change in concentration. Okay, on going to equilibrium, then equilibrium concentration, then define X as the yeah, equilibrium concentration, and you have to define X as the concentration mole per liter, okay, of the substance that reacts on going to equilibrium. Okay, then what is the step 3? Solve for X. Okay, then you have to substitute first, define X, and then solve for X. Third step. Okay. Suppose if it is quadratic, you can use quadratic to solve, quadratic equation to solve mathematically. Everyone knows about the mathematical solving for the quadratic equation, right? So calculate the equilibrium constants for the calculated value of X. Again, after that, you have to use this value of X to calculate the equilibrium concentrations. So results can be checked by putting the calculated value in the equation itself, whether it is satisfying or not. We can able to predict. So the same example is taken to show, okay, how to calculate the equilibrium concentrations. See this example. 13.8 gram of N2O4 was placed in a 1 liter reaction. Okay. Vessel at 400 Kelvin and allowed to attain equilibrium. Okay. So better placed all these things. So this reaction shows nitrogen tetroxide, right? N2O4. It is a heterogeneous, okay, heterogeneous equation. It is a gas. It gives nitrogen dioxide. Okay, 2 molecules of nitrogen dioxide. It is given, and you need to the total pressure also it is given Kc and Kp. You need to calculate and partial pressure also. Okay, so you know the equations, ideal gas equations. PV is equal to nRT. Volume is given as 1 liter, and molecular mass is given. You have to calculate the number of moles. No, molecular mass you need to find out that you know, right? 2 into 14, right? 2 into 7 plus 4 into 16. So it will be 4 into 16, that is equal to 92, right? So 92 gram. It is given as 38.8 gram of mole, right? So how many number of moles we can able to find out? Out of 13.8 gram, you have to divide 92 gram. Then you will be getting the number of moles. So the number of moles will be 0.15 gram of the 1.5 of the gas, total mole. Okay. Gas constant and this and all will be given in a question paper as a hint. Okay. Then temperature is 400 Kelvin. You have to substitute and find out the pressure. Okay. So volume is 1 liter and then substitute everything. Then this is the pressure, 4.98 baric pressure. Okay. So it is the initial pressure. You know that it is the reversible reaction. Then if X number of moles, we have to consider X, right? What is the third step we saw? In the second step itself, we saw we have to define Ex in the equation. Okay. So how you can able to define Ex? So there is a formula. How you can define Ex? The X number of moles are now converted into a product. So X is converted into product. So it will be 4.98 means the pressure now at equilibrium is 4.98 minus X. So here it will be 2X baric pressure. Okay. Since it is 2NO2, it is 2X baric pressure. And then pressure total will be pressure of nitrogen tetroxide, okay, and plus pressure of the nitrogen dioxide. Then it is given as the total pressure as 9.15, wherein the question itself given. Yeah, it is in bar only. So 9.15 minus, it is the total pressure. So 4.98 minus X is the pressure of the nitrogen tetroxide and 2X is the pressure of the nitrogen dioxide. So you'll be getting minus X plus 2X will be plus X. Then bring this here and find out X. You have solved for X. Sometimes it will be in the square. Quadratic equation also may come. That's what I said. In calculating the equilibrium constant, you have to follow the steps, right? In the third step, I said the quadratic equation may also be there. Okay. So you need to calculate using the quadratic X value by means of mathematical calculation. Okay. Then after that, you have to substitute the X here, right? Okay. Then here X you found, then substitute the X and find out the individual pressure. Okay. Then again find the equilibrium constant. Okay. This and all you know, equilibrium constant. It is 2 moles, so it is square, right? The product is molar concentration of the product by the molar concentration of the reactants. Okay. Reactants pressure is 0.81 or the product's pressure is 8.34, the whole square, right? 2 times, 2 molecules. So it will be 85.87. Then find out Kc here. Kc is, you know, Kp value find out, R value and T value and do everything. And then what is this actually? Kc value. Okay. So substitute and find out the value. I hope everyone knows this simple calculation. It is very easy only. Okay. Yeah. Then is that remaining? Okay. This is also the same. You have to calculate the composition of the mixer at equilibrium. Okay. Go through it. You know all the procedure. First define X. Here you can find the X in the form of quadratic equation. Then use the quadratic formula. How to solve the quadratic equation? You can use the formula minus B plus or minus root of B squared minus 4AC by 2A. That formula also you can use it and find first solve for X and then find the individual one. Okay. So this is very important. Definitely you maybe ask some questions from this. Okay. Then here it shows the relationship between equilibrium constant, between the equilibrium constant K, right? Then reaction coefficient Q and Gibbs energy G. So this is the topic and the relationship will be how the delta G will, it is given here. So the mathematical expression is not derived. Derivation is not shown in your book, but the final expression is given here. Like delta G is equal to delta G naught plus RT ln Q. Then delta G naught, what is this delta G naught? Delta G naught is negative RT ln K. Okay. If delta G is negative, then the reaction is spontaneous and proceeds in the forward direction. If delta G is negative, you know, this delta G naught is negative in nature. If it is forward, then the present value will be negative. If it is positive, it is not spontaneous. You know the spontaneous reaction. Rusting a fire is a spontaneous reaction. Okay. Formation of calcium hydroxide, this and all, the slate line. So this and all, the non-spontaneous reaction. So non-spontaneous reaction, if delta G is positive, and instead as reverse reaction, would have a negative delta G, the products of the forward reaction shall be converted to the reactants. Like that, it will be like a reverse reaction. See how it will be. What is the major difference? Delta G, if delta G is negative, then the reaction will be proceeding in the forward direction, right up. If delta G is positive, then the reaction is considered non-spontaneous. Okay? And instead, as reverse reaction would have a negative delta G, the products of the forward reaction, the product of the forward reaction shall be converted into the reactant. Same. Okay, it is the reverse reaction. Delta G is 0 means, it achieved equilibrium. Hmm? So this is all about, So ln K, from this you can able to calculate minus delta G naught by RT. If you are taking antilog on both sides, it will be K. Here it shows negative ln K, ln of delta G naught by RT. Then you need to find out ln of delta G naught by RT. Bring this negative to the power of minus 1. So if it is minus 1 means you can interchange this delta G naught. Okay? Is it clear for you? Is it clear for you? Then, so this is what explained here. If you are taking exponential on both sides also, it is easy for you to understand how it is explained. If you are taking an exponential on both sides, taking antilog also one type of method, then take exponential, then it will be e power ln k equal to e power minus delta G naught divided by RT. Okay. So here also the same exponential you are taking. So exponential and ln will cancel. So k is equal to e power negative delta G by RT. Okay. So keep this in your mind. This is very important. Here also you can able to understand how the delta G value. You can interpret all the terms based on delta G naught, which is negatives, okay, less than 0, then greater than 0. So based on the exponential thing, you can find out the k value. How the k value is. K is greater than 1, less than 1, like that. We can able to see. Okay. So go through it, and based on this, the problem also given. So it shows the relationship between the delta G, value of delta G, okay, and then equilibrium constant. So delta G is all knows about, it is Gibbs free energy, okay, then equilibrium constant, and then reaction coefficient, everything. So I taught you from your NCERT book itself, okay. So don't worry, you have to go through all these stuff. Then we'll see factors affecting equilibrium. So what are all the factors affecting equilibrium? Okay. So there are three main factors which affects the state of equilibrium. Okay. They are concentrations. Three main factors. Okay. Concentration, temperature, and pressure. Okay. So Lee-Chatelier principle. What is that principle? Lee-Chatelier principle. It's a scientist name. Lee-Chatelier principle. In this principle states that the equilibrium, if there is change in at equilibrium, for example, what it states that at equilibrium, okay, if there is change in concentration, pressure or temperature of the system, concentration, pressure or temperature of the system, the equilibrium will shift in such a manner to counteract the change. Got it. So what is the Le-Chatelier principle? If there is any change in this particular factors at equilibrium condition, it talks about the equilibrium condition. The equilibrium will shift in such a manner to counteract the change. Okay, equilibrium will shift. Okay, based on the change. So, what is the effect of change in concentration? You know now what is Le-Chatelier principle. Let me repeat again. At equilibrium, okay, all of you take down. It states that at equilibrium, if there is a change in concentration, temperature, and pressure of the system, the equilibrium will shift in such a manner to counteract the change. The equilibrium will shift in such a manner to counteract the change. Got it? So then, the effect of change of concentration. What is the effect of change of concentration? This is also second one. We can see the effect of change of concentration. So what is the effect of change of concentration? At equilibrium, the concentration of one of the reactants is increased. For example, okay, if at equilibrium, the concentration at equilibrium, okay, the concentration of one of the reactants is increased, the equilibrium will shift in the forward direction. Okay, if the concentration of one of the reactants increased, the equilibrium will shift in the forward direction and vice versa also. Okay, if A plus B is there, the concentration of A and B, okay, if this concentration is increased, then its equilibrium may shift. Okay, this shift, which is in the forward direction. Okay, the shift is in the forward direction. That means it is the equilibrium may achieve after some time the product is formed. Okay, it is not 50-50. We cannot say it is 50-50 like, okay, if there is a pressure or concentration. We can say if the concentration increases, the formation of product, such a product is somehow it is delayed. Okay, that means forward direction means equilibrium shifts to the forward direction and vice versa also possible. Okay, if it is decreased, if one of the concentration is decreased, the shift will be towards the reverse direction. Okay, so what is the effect of change of pressure? Next one, effect of change of pressure. Okay, change in pressure, like that also you can say. So students, keep in your mind, what is the effect of change in pressure? There is no effect of pressure on equilibrium. Okay, there is no effect, okay, of change in equilibrium. What it says, when there are some same moles of reactants and products. See, for example, N2 plus O5 or O2. Okay, N2 plus O2, it gives 2 NO2. NO, nitrous oxide, right? Nitrogen plus oxygen. It gives nitrous oxide. Here you can say, okay, if there is no effect of pressure in equilibrium, when there are same moles of reactants and products, okay, say for example, same moles of reactants and products, then there is no change in pressure. When there is a change in the number of moles, for example, here there is no change. No change in the number of moles. Okay. There is no change in the number of moles. There is no shift. Okay. There is no effect of pressure. Okay. Then, for example, N2 plus 3H2, it is reversible. Okay. It gives 2NH3. Okay. Here, what will happen? The equilibrium will shift. Here, you can able to see there is difference in the number of moles. Okay. There is difference in the number of moles of the reactants and the products. Okay. Then what will happen? The equilibrium will shift in the direction having a smaller number of moles. Okay, when the pressure is increased, suppose when the pressure also increased, the equilibrium shift will towards the smaller number of moles, where the smaller number of moles will be. Okay, here we can say the equilibrium will shift to the smaller number of moles. So here it is high pressure and high yield of NH3. Okay, vice versa also possible. Can you able to understand this? So how the equilibrium will shift? When there is a change in the number of moles, the equilibrium will shift in the direction having a small number of moles when the pressure is increased. But here the pressure has to be increased. Pressure should be high. Then NH3, the yield of NH3 also high. Yield of NH3 also high. Got it? So when the pressure is increased, the equilibrium will shift in the direction having a small number of moles. If the equilibrium shift in the direction of the small number of moles, definitely the production of NH3 will be increased. Got it? And vice versa also. Okay? So here, if the product side is the smaller number of moles, then the equilibrium shift towards this. Then the yield of NH3 will be reduced. Okay? Then the pressure will be decreased, right? The pressure of the reactants will be decreased. So this is the effect of change in pressure. So in all these steps, the vice versa is true. Okay. Then we'll see the next effect. Effect of temperature. This is common thing. Effect of temperature means when the process is, you know all about endothermic, exothermic. Okay. So if the pressure is, sorry, temperature, effect of temperature. Okay. When the process is exothermic, low temperature promotes forward direction. Exothermic means when the process is exothermic, okay, low temperature promotes forward reaction. Got it? Exothermic means it is releasing the temperature. When the process is endothermic means it is observing the temperature. So high temperature will be there. It promotes formation of products. Got it? Then effect of addition of inert gas. This is very important. Next effect is what is the factor affecting? Effect of inert gas. Adding inert gas. Inert gas addition or okay, if inert gas is added to constant pressure, so for example, you are keeping the pressure as constant pressure, okay, then it will increase the volume of the system. Okay, if you are adding the inert gas at constant pressure, it will increase the volume of the system. Therefore, the equilibrium will shift in the direction in which there is an increase of the number of moles. Okay, there will be increase in the number of moles. This is very important. Okay, so inert gas, if you are adding inert gas, so how you are adding inert gas? So inert gas at constant pressure, then the volume will increase and also therefore the equilibrium will shift in the direction in which there is an increase in number of moles of gases. Okay, then if an inert gas is added at a constant volume, for example, if it is at constant volume at the system, the relative molar concentration of the substance will not change. Hence, the equilibrium state of the reaction remains unaffected. Okay, at constant value, and it is unaffected. Okay, then effect of catalyst we will see. Okay, effect of catalyst. The presence of catalyst does not change the state of equilibrium. You know, it is added to enhance the reaction. It does not change the state of the equilibrium. It simply speeds up the process of equilibrium. Simply speeds up the process of equilibrium. Okay, the process of equilibrium. Okay. Then we can see Le-Chatelier's principle applicable to physical equilibrium, right? Effect of pressure on solubility. Okay, you know what is the Le Chatelet principle? We saw at equilibrium.